Okay, let us start the lecture. So today we will do some theorems on Lebesgue integration. Some fundamental theorems. These are actually the pillars of Lebesgue integration. The first theorem is given by Levy. Okay, it's actually a monotone convergence theorem. So Levy's theorem. This is our first theorem on integration. That's Levy's theorem. The statement is assume that a sequence Fn of integrable functions satisfies functions satisfies Fn lesser or equal to Fn plus 1 almost everywhere. That's it's monotonic increasing almost everywhere for each n. And limit of integral of Fn is finite. Then there exists an integrable function f. Then there exists an integrable function f such that obviously it's a function from x to r, such that Fn increases to f almost everywhere. That means limit of Fn is this function f almost everywhere, and this limit of integral of Fn is equal to, or you can say, and integral Fn, the limit of this, it increases to integral of f, or we can say this limit of integral of Fn is equal to integral of limit of Fn. Okay, proof of the theorem. So this is very important theorem because it guarantees the existence of integrable function. So we don't have a limit function, but we have given a sequence of increasing integral functions and satisfying this condition, limit of integral of Fn is finite. Then we can find a function f which is the limit of this Fn, and that function is integrable, satisfying this property. Limit of integral of Fn is equal to integral of limit of Fn. Okay, so we replace this sequence Fn by Fn minus 1, or without loss of generality we assume that each Fn is, so assume that, then we do the general case. Okay, assume that 0 less or equal to Fn and less or equal to Fn plus 1. So let's take this assumption. Assume this holds, okay, for all, and this sequence is non-negative. And also we can assume that next we assume that also we can assume that this 0 is less or equal to Fn of x less or equal to fn plus 1 of x for all x belongs to x, हर किसी x के लिए, यहाँ पर actually almost everywhere है, but we can assume that this property holds throughout x because our conclusion is regarding the integration में almost everywhere से कोई फर्क नहीं पड़ता. तो अगर ये almost everywhere नहीं होगा तो you can take a subset A of x where this property does not hold and the measure of that set is 0. फिर आप उस सेट की कॉम्प्लीमेंट, उस सेट का जो कॉम्प्लीमेंट होगा उस पर ये इनइक्वालिटी होल्ड होगी, आप उसी पर ये इस रिजल्ट को कीजिए. आप वहाँ पर लिख सकते हैं fn increases to f everywhere on that set. So that's a subset of x, वो भी मेजर स्पेस है and because the subset of a major space is a major space, तो वो भी एक मेजर स्पेस ही होगा. तो वहीं पर आप ये सारी चीज़ें प्रूव करोगी और जब आप फाइनल कंक्लूजन आपको मिलेगा ना इंटीग्रल ओवर दैट सेट ए, आप उसको लिख सकते हैं इंटीग्रल ओवर द सेट ए प्लस इंटीग्रल ओवर ए कॉम्प्लीमेंट, क्योंकि उस दूसरे सेट का मेजर 0 है. सो दैट यू कैन डू, you can assume that this holds throughout because you can remove the null set. null set remove करने से इंटीग्रेशन पर कोई फर्क नहीं पड़ता है. null set को अगर रिमूव करेंगे, इसको आप इंक्लूड करो या रिमूव करो, इट्स वन एंड द सेम. पहले आप इसको रिमूव कीजिए तो आपको ये जो प्रॉपर्टीज़ है, दिस प्रॉपर्टीज होल्ड एवरीवेयर ऑन दैट सेट. जब आपने नल सेट को रिमूव किया, जो रिमेनिंग सेट है वहाँ पर ये प्रॉपर्टी होल्ड होगी एवरीवेयर, और इसी पर आप रिजल्ट को प्रूव कीजिए और फिर इंटीग्रेशन में आप उस नल सेट को वापस आप इंक्लूड कर सकते हैं, क्योंकि इंटीग्रेशन पर जो है ना नल सेट का कोई असर नहीं होता. वेदर यू कैन रिमूव द नल सेट, वेदर यू रिमूव द नल सेट और include the null set to your given space, it will not affect our integration. Okay, so we can assume that this inequality, this property of fn holds throughout x. तो पहली assumption हमने ली it's greater or equal to 0, वो मोनोटोनिक इंक्रीजिंग तो है ही ऑलमोस्ट एवरीवेयर, तो हमने ये भी मान लिया कि ये ग्रेटर इक्वल टू 0 भी है ऑलमोस्ट एवरीवेयर. और सेकंड में मैंने कहा कि आप ये जो प्रॉपर्टीज़ है इस प्रॉपर्टी को एज्यूम कर सकते हैं थ्रूआउट. तो जो फर्स्ट वाली मैंने एजम्पशन की है नॉन नेगेटिव, इसको मैं आगे डिस्कस करूँगा. ये हम फिर जनरल केस में भी कर सकते हैं. इफ़ इट्स नॉट ग्रेटर इक्वल टू 0 वी कैन स्टिल डू दिस, दैट विल डू फर्स्ट वी डू दिस केस इफ इट्स ग्रेटर इक्वल टू 0. So 0 is lesser equal to fn x, lesser equal to fn plus 1x for each x in x, and let I be the limit of the integral, which is finite. It's given in the statement, limit of integral of fn, and that's finite. I is finite. I से मैंने इस इंटीग्रल को डिनोट किया है, इस लिमिट को मैंने डिनोट किया I से. So this fn x is monotonic increasing, so we can define its limit. The limit may be it will never oscillate. आपके पास ये है, देखिए आपके पास ये है, आपके पास fn x lesser equal to fn plus 1x. तो इसका जो लिमिट होगा ना, लिमिट ऑफ fn x, दिस विल एग्जिस्ट ऑलवेज, लिमिट, because it is monotonic increasing for each x. So let's take its limit is that will obviously depend on x को vary करोगे, you will get the different limits, but for each x this is monotonic increasing limit, this is monotonic increasing, so its limit exists whether finite or infinite, and that limit will always depend on x. If you change x you will get the different limits. So let's denote that limit by g of x. So this g of x is a function of x, but g of x it may take infinite values also, because for some values of x the limit of fn x may be infinite. For some values of x it may be infinite. Okay, so but we have a limit of this sequence. It may be infinite or finite. monotonic increasing का sequence जो होती है इसका हमेशा लिमिट होता है, वो कभी भी ऑसिलेट नहीं होगी. तो ऑसिलेट का मतलब है क्या है कि पहले भी ये सीक्वेंस आगे जाएगी फिर वापस आ जाएगी, बट इट इज मोनोटोनिक इंक्रीजिंग, इसका लिमिट हमेशा आगे ही होगा. सो दैट लिमिट मे बी फाइनाइट और इनफिनाइट. ओके, since fn x okay, since fn of x lesser equal to fn of fn plus 1x. Therefore limit n approach to infinity. This is true for all x, okay, for all x, okay. So therefore limit n approach to infinity fn x exists in, not in r, in r star, it may be infinite for all x belongs to x. So let's denote this limit by let limit n approach to infinity fn x is equal to g of x, and this g of x is in r star. So that is g is a function from x to r star. It's not a real valued function, it is extended real valued function. And we will see that the set of the points of x where g of x is infinite, that set is a null set, okay. We will show that that's a null set. Let E be this set it is the set of the points of x such that g of x is where this limit is infinity, okay. We show that E is measurable, and we show that E is सबसे पहले आपके पास ये फंक्शन आ गई आपके पास लिमिट एन अप्रोच टू एफ एन एक्स इक्वल टू जी एफ, बट दिस इज नॉट अ फंक्शन फ्रॉम एक्स टू आर. हमें एक्स टू आर एक्चुअली फंक्शन चाहिए, तो वो हम इसी फंक्शन से कंसिडर करेंगे, इसी जी से. हमें कोई एफ चाहिए विच इज द लिमिट ऑफ एफ एन एक्स, बट दैट फंक्शन शुड बी फ्रॉम एक्स टू आर. So we show that E is measurable and mu star of E is equal to 0. 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 Okay. So first we verify that first we verify that E is equal to intersection I runs from 1 to infinity, and then union and runs from 1 to infinity of the set x belongs to x such that fn x greater than I. ये हम पहले वेरीफाई करेंगे. अगर हमने ये वेरीफाई कर दिया, that means E is measurable, because each set, since fn x is measurable, therefore this set is a measurable set for each I and for each n. So the union with respect to n is measurable, then intersection with respect to I is measurable, because class of measurable sets is S sigma algebra. So let's take x in the intersection and over union. Let x belongs to intersection I runs from 1 to infinity, then union n runs from 1 to infinity of the set x belongs to x such that fn of x greater than I. fn of x greater than I. So this is true if and only if x belongs to union and runs from 1 to infinity. X belongs to x such that fn x greater than I for all I, because its intersection is with respect to I. So which is true if and only if, now union is with respect to n, it means that x belongs to the set x belongs to x such that fn of x greater than I for some n and for all I greater or equal to 1 for some n. Okay, so that's true because since fn is monotonic increasing, fn x is greater than I, so that means fn plus 1x is also greater than I, fn plus 2x is also greater than I. So that's true if and only if x belongs to the set x belongs to x such that fn of x, sorry, let's write it as fm of x. Okay, fm of x greater than I for all m greater or equal to n and for all I greater or equal to 1. So for all I greater or equal to 1 we have m such that fm x is greater than I, which means that limit of fn x is equal to, so this is true if and only if limit of fn x is equal to infinity. Okay, so that means g of x, this is true if and only if gx is infinity. This is true if and only if gx is infinity, and which is true if and only if x is in E. So thus is equal to the intersection I runs from 1 to infinity, then union n runs from 1 to infinity of the sets x belongs to x such that fn x greater than I. So which implies that E is measurable. E is measurable, which implies that E is measurable. Okay, this set is measurable, which implies that the set is measurable. Okay, so now we show that mu star of E is equal to 0. Since fn x greater or equal to 0, since fn of x is greater or equal to 0 for all x belongs to x, so therefore, and it's also integral, therefore fn is an upper function, is an upper function for all n greater or equal to 1, because every non-negative integrable function is an upper function. So it's an upper function. So therefore for each I, since fi is upper function, for each I we can find I of step functions. So thus for each I, for each I greater or equal to 1, there exists, thus for each I in I there exists a sequence, phi and I of step functions. step functions such that 0 less or equal to phi and I, because each fi is greater or equal to 0, and this will increase to fi almost everywhere. This limit is almost everywhere. Now for each n we define a step function. For each n greater or equal to 1, define psi n is equal to join of phi and I runs from 1 to n. Then this phi n, it's psi n. Then psi n is a sequence of step functions such that you can easily verify. Then psi n is a sequence of step functions. Then psi n is a sequence of step functions. Psi n is a sequence of step functions such that this limit of psi n is same as limit of fn, and that's equal to g. So therefore, since psi n is monotonic increasing and its limit is g, so therefore this psi n, it increases to g, because psi n is less or equal to psi n plus 1, because psi n is less or equal to psi n plus 1. This limit is almost everywhere, obviously. Psi n is less or equal to psi n plus 1 almost everywhere. So limit of psi n is same as limit of fn, but limit of fn is g, and psi n is monotonic increasing. That means psi n increases to g almost everywhere. So now we see that now let's write it as we claim that limit of integral of psi n is same as limit of integral of f. Okay, so we have the following. We have this psi n, which is equal to join of phi and I runs from 1 to n, and that's equal to phi n1 join phi n2 join phi nn. But phi n1 is the generating sequence for f1, so it's less or equal to f1, because f1 is a limit of phi n, increasing limit, and phi n2 it's a generating sequence of f2, so it's less or equal to f2. Okay, and join fn. Again, this fn is it's an increasing sequence, so join of f1 f2 fn, it's equal to fn. So psi n is less or equal to fn. Both psi n and fn, they are integral functions, which implies that integral of psi n is less or equal to integral of fn. So here you can write there everything, it's almost everywhere. Okay, which implies that limit of integral of psi n is less or equal to limit of integral of fn. Name it 1. Now you want the reverse inequality actually. So again we have this fm join psi n. Let's see this. Let's take the limit with respect to n. It will increase to with respect to n. Okay, fm join g, because limit of psi n is g. But the limit of fm is also g. It's the increasing limit, so fm is less or equal to g. It's equal to fm, because fm also increases to g. Limit of fm is g. Okay, yeah, so let's apply the integration on both sides. So this limit of this is equal to this one. So it means that fm join psi n is lesser equal to fm for all n greater or equal to 1. This is also true for each m. So that means the integral, because both are integral functions, is lesser equal to integral of fm for all n greater or equal to 1. But then let's apply the integral with respect to n. Limit n approach to infinity, integral fm join psi n is lesser equal to integral of fm. So for each m it's lesser equal to, okay, for each m it's always lesser equal to fm. So this psi n join meet psi n, fm meet psi n, okay. So the limit is always lesser equal to, limit of the integral will always be lesser equal to integral of fm, integral of fm. Okay. Also let us see this. Also this fm meet psi n is lesser equal to psi n. Okay, for all n and m. This is also true. So now let's find, let's take this integral of fm. Let's see this. Now let us see this integral of fm. It's equal to that you have seen. It's equal to limit n approach to infinity, integral of fm meet psi n. But fm meet psi n is जो आपने अभी देखा, it's lesser equal to limit n approach to infinity, integral of psi n, because fm meet psi n is lesser equal to psi n. Okay, so this is true for each m, for all m, okay, for all m greater or equal to 1. So which implies that limit m approach to infinity, integral of fm is lesser equal to limit n approach to infinity, integral of psi n. You can use the n here also. Limit n approach to infinity, integral of fn is lesser equal to limit n approach to infinity, integral of psi n. So name it second. From first and second we can see the limits are equal. So let's see the first. What's first? First is this one. This is first. Limit of psi n is lesser equal to limit of integral of psi n is lesser equal to limit of integral of psi n, okay, and here it's limit of integral of fn. So by combining first and second, by combining first and second, we get limit of integral of psi n is equal to limit I can write here n approach to infinity, limit n approach to infinity, integral of fn, but this thing is I, this limit which is finite, okay. So these two are equal. This is from first and second, and this is given in the hypothesis. This is I and I is finite. This limit is finite, okay. So the limit is finite. So now for each k, now for each k greater or equal to 1, we verify this thing. Psi n meet k times chi e. This is an increasing, because psi n is increasing. This will increase to k times chi e, okay. So obviously the limit is fine twice, so we have to fix x actually. So in the first case we take x is in I, in the second case and we take x is not in E. X is in E and x is not in E. If x is in E, then what psi n meet k times chi E? It's just psi n meet k. And what's the limit of this? Now this k is constant. The limit of this will increase because limit of g is g. Limit of sin is g. It's g meet k. G meet k. But since x is in E, whenever x is in E, g of x is in infinity. So this value is infinity. So what is the meet? Meet is the k actually. This limit is k. And k is same as k times chi E because x is in E. So psi n meet k chi E, it increases to k chi. So psi n meet k times chi E increases to k times chi E in this case if x is in E. And in the second case, if x is not in E, if x is not in E, if x is not in E, then let us see this psi n meet k times chi E, it's equal to psi n meet 0, but this sign is greater or equal to 0. It's a non-negative function, and the meet of non-negative with 0, it's equal to 0, which obviously increases to 0 because it's a 0 sequence, and this 0 is same as k times chi E because chi E is 0 here, x is not in E. So psi n meet k times chi E, it increases to k times chi E. So thus we have this psi n meet k times chi E, it increases to k times chi E in every case. Okay, यहाँ पर आप लिख सकते हैं in this case also. So that this is true, this is true. Okay, this one is true. Now you can apply the theorem 17.6. okay, by theorem 17.6 we have this k times mu star of E, k times mu star of E, the limit of this sequence is equal to the limit n approach to infinity, the integral of that sequence. What's the sequence here? The sequence is psi n meet k chi E, psi n meet k chi E. Okay, psi n meet k chi E, psi n meet k chi E, but psi n meet k chi is less or equal to psi n, it's less or equal to limit n approach to infinity, integral of psi n, and this is finite. This is equal to I, which is finite. So which implies that k times mu star of E is finite for all k greater or equal to 1, and this is only possible if mu star of E is equal to 0. If it is positive, then the k times mu star of E will approach to infinity if k approaches to infinity. So this means mu star of E must be equal to 0. So that means is a null set. E is a null set. So that proves the second property of E. Now we come to the proof of the theorem. Now actually we have to construct the function f. So let's define that function. Now define this function. Now define f from x to r. Define f from x to r by f of x equals to g of x if x is not in E, where it's finite. okay, क्योंकि E पर gx इन्फिनिटी है, तो x अगर E में नहीं होगा, इस केस में fx में gx ही होगा. And and take its value 0 when gx is infinity में. So when x is in, क्योंकि इस केस में g of x infinity होगा तो मैं fx का वैल्यू 0 होगा. So therefore this f from x is a function from x to r. It's a function from x to r. It's a function from x to r. Okay. So therefore, so you write here this. Then this f is a function from x to r, and this fn, it increases to f almost everywhere. It increases to f almost everywhere. So it's a limit of this. So fn is a sequence of upper functions, and its limit is f. So by theorem 21.6 you can see that theorem 21.6 in which you have seen that if f is a function from x to r, and if there is a sequence of upper functions such that fn increases to f almost everywhere, then limit of integral of fn is, and limit of integral of fn is finite, then f is integrable, then f is an upper function. So by theorem 21.6 इससे पहले जो सेक्शन हमने किया ना अपर फंक्शंस का, वहाँ से by theorem 21.6 f is an upper function. F is an upper function. F is an upper function है, and an integral of f is equal to limit and approach to infinity integral of f by that theorem. Okay. So f is upper means upper function that you can write in brackets, hence integrable. Okay, hence actually I meant integral function. Every upper function is integrable, and hence integrable. So by theorem 21.6 f is an upper function, hence integrable, and integral of f is equal to limit of integral of fn. That proves the theorem completely. That proves the theorem completely. So the next theorem is following from this theorem. It follows from this theorem, next theorem. Let fn be a sequence of non-negative integrable functions. Let fn be a sequence of non-negative integrable functions. Non-negative integrable functions such that summation n runs from 1 to infinity integral of fn is finite. Then this sum is also integrable, sum function. Then summation fn n runs from 1 to infinity is integrable, and this f of the integral of some function, sorry, it's integral of some function. Then integral of some function fn is equal to sum of the integrals of function. This proof, it follows from previous theorem actually. So let's define Gn. Let Gn is equal to summation n runs from 1 to infinity, sorry, its summation k runs from 1 to n. Summation k runs from 1 to n fk. Then Gn is integrable because finite sum of integrable functions is again integrable function, and it's also monotonic in increasing because you are adding the positive functions, as fn is a non-negative sequence. Okay, so g1 is f1, g2 is f1 plus f2. You are adding non-negative function, that means g1 must be less or equal to g2. So then this gn is is a sequence of integrable functions. Sequence of integrable is a sequence of integrable functions. Is a sequence of integrable functions such that gn is less or equal to gn plus 1. Gn is less or equal to gn plus 1. Also let us see this. तो gn जो एक नई सीक्वेंस है ना इंटीग्रल फंक्शंस की, इसने एक कंडीशन लेवी थ्योरम के सेटिस्फाई की, दैट इट्स मोनोटोनिक इंक्रीजिंग. हमें भी सेकंड कंडीशन चेक करनी है. लिमिट एंड अप्रोच टू इंफिनिटी इंटीग्रल ऑफ gn, दिस शुड बी फाइनाइट. दिस इज इक्वल टू लिमिट एंड अप्रोच टू इंफिनिटी इंटीग्रल. व्हाट्स gn? gn is summation k runs from 1 to n एफ के. अब क्योंकि ये फाइनाइट सम, इसको बाहर निकाल सकते हैं. लिमिट एंड अप्रोच टू इन्फिनिटी समेशन के रन्स फ्रॉम 1 to n इंटीग्रल ऑफ एफ के. So this is same as when I applying this limit. This is equal to summation k runs from 1 to infinity integral of f k. अगर आप इसको n में कन्वर्ट करना चाहते हो for your simplicity, so summation n runs from 1 to infinity fn, but this is your integral, okay, integral of this, but this is finite, it is given, this is finite. तो ये जो sequence है ना gn, the sequence of integrable functions, it satisfies both the conditions of Levy's theorem, so you can apply the Levy theorem. So by Levy theorem the limit of this sequence exists. So by Levy theorem, by Levy's theorem, the limit of this sequence, limit of gn, which is equal to summation n runs from 1 to infinity fn, is integrable, is ये integrable होगी by Levy's theorem, and the integral of this and integral of this function, this limit function, that was f in our previous theorem. Actually, limit of the integral of the limit function, that's summation n runs from 1 to infinity fn, it's equal to the limit and approach to infinity integral of gn. Okay, integral of limit of gn, this limit of gn is equal to limit of integral of gn, that's equal to limit and approach to infinity. What's gn? gn is summation k runs from 1 to n fn. अब इस सम को बाहर निकाल सकते हो, so then you can apply the limit, it is equal to summation n runs from 1 to infinity integral of fn. यही आपको प्रूव करना था. So this proves the theorem completely. Now our next theorem is Fato's lemma. Our next theorem is Fato's lemma. So the next theorem is Fato's lemma. Fato's lemma. Let fn be a sequence of integrable functions. Let fn be a sequence of integrable functions of integrable functions such that fn greater or equal to 0 almost everywhere, for each n, for all n greater or equal to 1, and limit inferior of integral of fn, limit inferior integral of fn defines it is finite. Okay, integral of fn is finite. Then limit inferior of fn defined as an integral function. Then limit inferior of fn defined as an integrable function. Defined as an integrable function. And integral limit inferior of fn is less or equal to limit inferior integral of fn. So this is the statement of Fatou's lemma. So this is the condition here. Okay, the limit inferior of integral of fn is finite. आपको इसमें लेविस थ्योरम यूज करनी है. तो लेविस थ्योरम के लिए आपको वो नई सीक्वेंस कंस्ट्रक्ट करनी है which satisfies the properties, both the properties of लेविस थ्योरम. Then you apply the लेविस थ्योरम. और वो आप कंस्ट्रक्ट कर सकते हो विद द हेल्प ऑफ दिस. ये जो है ना लिमिट इंफीरियर ऑफ इंटीग्रल ऑफ fn इज फाइनाइट, जो यहाँ पर हमने लिखा है, इसका यूज करके हमें वो सीक्वेंस मिल सकती है. So let's prove this theorem. So our aim is to construct a sequence Gn such that Gn satisfies both the conditions of Levi's theorem. So first, without loss of generality, we may assume that we may assume that this fnx is greater or equal to 0 for all x in x and for all n greater or equal to 1. Now given n, let's define this Gn. Define Gn. It's equal to infimum of fix such that I is greater or equal to n. So what's then G1? G1 is the infimum of fi where I is greater or equal to 1. So infimum of the set f1, f2, so on and so forth. And G2 is the infimum of the set f2, f3, so on. तो ये set decrease हो रहा है अगर आप n के values को increase कर रहे हो. So then the infimum will increase क्योंकि set decrease हो रहा है, infimum increase हो रहा है. That means Gn is increasing sequence. Then Gn is increasing. और fi जो है ना ये इंटीग्रेबल फंक्शन है, and infimum of integrable functions is again an integrable function. So then Gn is a monotonic increasing sequence of integrable functions. Gn is measurable, or cannot say integrable. Gn is measurable. Sorry, Gn, because these fi's are integrable, therefore they are measurable, and infimum of measurable functions is again a measurable function. Then this Gn, it's a sequence of measurable functions. Is a sequence of measurable functions. Is a sequence of measurable functions such that this Gn of x is less or equal to Gn plus 1 of x for all n greater or equal to 1 and x belongs to x. A first property, it's monotonic increasing, and it is the infimum of G1 is the infimum of f1, f2, so on. G2 is the infimum of f2, f3, so on. So G1 is infimum of f1, f2. Okay, that means G1 is less or equal to f1, it's less or equal to f2, so on and so forth. इसी तरह से जो G2 होगा क्योंकि ये infimum of f2 से start हो रहा है G2 के लिए, so that means G2 is infimum of f2, f3, so on and so forth, which means that G2 is less or equal to f2. So in general Gn is less or equal to fn. So Gn obviously non-negative ही है ये, because you are taking the infimum of non-negative functions, non-negative numbers in fact. So 0 less or equal to Gn less or equal to fn. Monotonic increasing है और इस property को satisfy. But since our fn is integrable, 0 is integrable, it's a constant function, so therefore any measurable function which lies between two integrable functions is also an integral function. So then Gn is integral. Then Gn is integrable for all n greater equal to 1. तो आपके पास एक इंक्रीजिंग सीक्वेंस मिल गई है इंटीग्रेबल फंक्शंस की, जो कि फर्स्ट कंडीशन है लेवी थ्योरम के लिए. अब सेकंड कंडीशन क्या है? लिमिट ऑफ इंटीग्रल ऑफ Gn मस्ट बी फाइंड. अब हम वो कैलकुलेट करेंगे. व्हाट इज द लिमिट ऑफ इंटीग्रल ऑफ Gn? सो नाउ लेट्स सी दिस. नाउ इंटीग्रल ऑफ Gn, it's less or equal to integral of Fn for all n, because Gn is less or equal to Fn. So let's apply limit inferior on both sides. Limit inferior of integral of Gn is less or equal to limit inferior of integral of Fn. But this Gn is monotonic increasing, so integral of Gn is also monotonic increasing. So that means this sequence it always converges. It will never oscillate. It always converges either to finite number or to infinity, but it cannot oscillate. So that means limit inferior of this sequence and the limit superior of this sequence, they are same and they are equal to the limit. This implies limit of integral of Gn, it's less or equal to limit inferior of integral of Fn. But this thing is given, it's finite. तो Gn ने दोनों कंडीशन सेटिस्फाई की है लेवीज थ्योरम की. नाउ यू कैन अप्लाई द लेवी थ्योरम. So thus by Levy's theorem there exists an integral function. Thus by Levy's theorem there exists an integrable function g such that Gn increases to g almost everywhere. Okay, so Gn increases to g almost everywhere. So that means your limit of Gn, that is limit of, or you can say g is equal to limit of Gn. You can write it like this. G is equal to limit of Gn. This is equal to limit, it's an approach to infinity. What's Gn? Gn is the infimum of Fi where I greater or equal to n. But this by definition it's equal to the limit inferior of Fn. This is the definition of limit inferior. Okay, so g is equal to the limit inferior of Fn. So hence, since g is integrable, hence limit inferior of Fn inferior. Okay, Fn is integrable. So also by Levy's theorem, we have what? We have integral of g, it's equal to limit n approach to infinity integral of Gn. So that implies what is this? This is limit. This is actually limit of Gn, or you can say g is actually limit infinity. हमने अभी देखा है. So you have seen that this is equal to what? This is equal to this thing. This is equal to limit inferior of Fn, it's equal to limit n approach to infinity integral of Gn. Okay, integral of Gn, name it 1. But Gn is less or equal to Fn. Okay, so this implies integral of Gn is less or equal to integral of Fn. Then you can apply limit inferior on both sides, because on this side a limit may not exist, it may oscillate. So we have to apply limit. We cannot apply limit actually. Here we apply limit inferior, but on this side limit inferior is equal to limit, because this one is monotonic increasing. So that means limit of integral of Gn is less or equal to limit inferior of integral of Fn. ये हमने इससे पहले भी लिखा है शायद इसी थ्योरम में. So one gives integral of limit inferior of fn is less or equal to, it's equal to limit of this integral, but limit of the integral is less or equal to limit inferior of integral of fn as required. As so this was Fato's lemma. So now we are in the next step we have this the Lebesgue dominant